Now, once again, I want to welcome you all to 2014 Maniac Talk series. Now, this year we have arranged very exciting speakers, more with a bias towards our leaders. So, next month, obviously, we are waiting to hear from Peter Hildebrand, and he's here, of course, before he heads out. So you have a lot of stories to tell us next month. And then, of course, Ann Thompson is coming in March. Okay. And of course, Jim Irons, I think, later on in the year, we'll plan again. So we are going to feature a lot of our leaders this year. And of course, we'll also try to get some people from the space community. We have been talking to Sam. So it's going to be an exciting year. So looking ahead, a very exciting year. So today's speaker, Bill Lau, of course, needs no introduction. But I asked Kim Young Kim, who has worked with him for many years. When I say many years, I mean about 17 years, to tell us about some of the insights of Bill Lau. Not necessarily talking about when he got his PhD, but some of the inner stuff that perhaps most of us would not know. So with those few remarks, Kim Young Kim, thank you.
Thank you, Charles. It is my great honor to introduce today's speaker. And as he said, I have had the privilege to work with him for over 17 years, actually starting from 1996. And I actually first met him in early 90s, as I think in 1992, when he visited Korea and gave a seminar at my department. And I was a student, and I still remember his second slide. Probably he doesn't remember the second slide. But the slide was was the back then very popular seasonal mean OLR. As a student, it's like it's a hidden object game to me. The speaker bring up that figure and say something about that, and I was aha kind of moment. And he started talking about that slide, and it lasted 15 minutes. I actually measured the time, and he covered starting from the score line to the NGO, to the annual cycle, to the El Nino, and all the way to the climate change with one slide. And that was like a longest hidden object game I ever witnessed. And that 15 minutes make him my role model. And shortly after that, actually, I haven't had an opportunity to come to visit him for 6 months. And in fact, Kathy last month actually found that letter I sent to him in September 1992. I'm thanking him to giving me an opportunity to come to visit. And actually, that was September 23rd, and week before I learned that about my father has a terminal cancer, so I couldn't come. But that one paragraph letter, I thanked him and what I want to work with him kind of thing. And I found, actually, I wish you could never found that letter because I found so many typos there and broken English. I really thanked him to hire me after 4 years. After 4 years from that point, even though my English was really, really terrible at the time. And speaking of English, actually, when I come to here, actually, I have an experience. We usually have a regular meeting, and one meeting is lasts 1 hour usually. And I still remember that day, after 1 hour meeting, he told me that, that's what you told me in the beginning. So he really actually tried hard to understand me for 1 hour. That shows me his character, because he's very generous, he's very understanding, and he is always engaged in the meeting, try to understand the things. He really liked to discuss. Even one time I realized that I made a mistake in the figure, and I explained that there was a mistake. And actually, he didn't give up. Actually, continued this discuss and tried to modify the image by try to imagination what's going to happen really if I did it correctly. So he really likes to discuss, engage, and he's very. No, I think nobody. I believe that no one sees him mad at anything. Right? It's that kind of character. And the one thing I want to say at the last is that people know probably that I'm going out with lunch with him and other two young scientists every day, even though we bring the lunch box to the cafeteria. So we talk about the families and science and the politics and also his favorite player RG3. But you know, since I'm going out with lunch with my boss and big boss of everybody, I kind of expected to learn something happy in the management. Right? But he's a character today. He never chit-chat or gossip about that. So those characters, I believe that he is very balanced in terms of science, in terms of management. It fit really well, in my opinion.
Okay.
So this is a picture of a Jesuit convent in Macau, okay? And that's a Portuguese colony. Okay, so let me take you back to history, 500 years back, okay, all the way back. So the Portuguese first set up a permanent trading post in Macau, which is a small place in the southern China in 1537 during the Ming Dynasty, okay, all the way back. And then Hong Kong was ceded to Britain as a colony in 1842 after the first Opium War, okay? And in fact, there was only the Hong Kong island itself. Later on, the new territory, if you've been to Hong Kong, actually later another war, that territory was ceded to Britain, the entire Hong Kong island, and it was ceded to Britain for 99 years, and that year is 1898. So that's why Hong Kong was returned to China in 1997 after its 99-year lease was up. The Hong Kong island itself was permanently ceded, but then, of course, what's the use of just the island itself? So that whole place was given back to Hong Kong in 1997. And then, formally Macau was ceded to Portuguese because of the war. I mean, all the Western powers come to China, they take over the place and everything. So and the Chinese government was really weak at that time, the Qing dynasty. And so they have to force to sign all these treaties, giving up all the port cities and everything. So that's the part of the history. And this one is the early 16th century trading routes of the Portuguese. You can see they come from Lisbon, across southern tip Africa, going to Goa. For people from India knows about that. Malacca, that's from Malaysia, and then to Macau, and then to Japan. So that's basically the Portuguese trading route at that time. So that is the long history. So this is the two places, the twin cities, so-called, that which I was born, and the other one I was brought up in. And one is a Portuguese colony, one is a Hong Kong, a British colony. So that's why early on, even though I'm not physically in Europe, I got a heavy dose of European culture and also education system. Okay, so that's where, and this is actually a very old atlas that was taken, in Amsterdam. Currently exists in Amsterdam Museum in 1655, that early part of China when they were the explorer, the European exploration of China. So back to my family history. Okay, my grandfather on the father's side was from southern China, from Zhongshan, which is actually the village where Dr. Sun Yat-sen, the founding father of China, some of you know, we were in that same village from southern China. Okay. And he was a mid-level official in the Qing dynasty, okay? And with the rank of some, it's not Juren, so those are Chinese, you know. This is not the top-level government. Well, you have all the Chinese, you have to get educated, then you pass a civil examination go to Beijing and take an exam, and then you will be ranked according to that examination. So he actually was one of the mid-level. It's like the third or the fourth level. They're like, I don't know how many levels, but the top one is the one that always remain to work in the central government, and the others will just go to different provinces and be the government officials and things like that. And in fact, in my family, actually in my brother's house, we still have a letter of commendation from the Qing dynasty, with the chop of the Qing dynasty, which were for my grandfather, who actually was responsible for mopping up some rebellion in southern China. Southern China is always very rebellious. We are considered kind of not the main part of China, so we are kind of the barbarians, kind of on the southern side. So my grandfather actually, we had like a 3x5 commendation in my brother's house that has the Qing dynasty chopping it for commendation for what he did. So we have kind of this family history. And then my grandfather on the mother side was a member of the Qing Zhonghui. The Chinese here know this is a revolutionary party that was from the same village, Zhongshan, because we're from Zhongshan. So obviously he has an association with Dr. Sun Yat-sen, and he actually started the revolution to overturn the Qing dynasty with a lot of help from the immigrants, Chinese immigrants in Hawaii, because there's a lot of the people in Zhongshan actually went to settle down in Hawaii. That's my grandfather on my mother's side actually settled down in Hawaii, actually had a family over there, but because Dr. Sun Yat-sen went to Hawaii to try to get the revolution going, Qing dynasty and things like that, he actually worked within an inner circle with Dr. Sun Yat-sen, the founding father of modern China, and the revolution took place officially in 1911, where the Qing dynasty was turned over, okay, to the Chinese. And he later returned to China, remarried, actually he kept two families. So I have distant relatives which are actually married to a local Hawaiian. So I have that part of the family which is away, but then he went back and remarried and had my mother. Okay, that's kind of the way back the family. My father, Liu Yixin, was first in the village to go to college. Okay, I mean we were from the poor village, and nobody go to college. Even though at that time higher education, well, it was kind of a modern thing to do, but mostly people get their education through the local colleges, private tutors and things like that. And he was an educator, and he became a government official in charge of agricultural affairs in Zhongshan. He taught Chinese and world history, Chinese literature in high school when he was in Hong Kong. Mother was also a high school teacher and homemaker. So that's my family history. And so here's where I came in. The parents actually, they went through a really tough time in their life because of the revolution, the Japanese invasion, and then World War II. Even though World War II ended in 1945, but there was a civil war going on in China. We have to take over by the People's Republic of China, the fighting between the communists and the nationalists. So the family was caught right in that kind of a war at that time. So being a national government official, when they learned that the communists from the north are coming, and then they will come to Nanjing and going to go south, then he knows that and then heard about the communists come and people get imprisoned, people get killed. So as a government official, he knows that his family is in trouble. So in a big hurry, he left in 1949 from Zhongshan. I don't know exactly how he came, and he just came to Macau. Actually, he left in such a hurry that he left part of the family behind. And naturally, he just took the older son and the younger son, which is two of my brothers, older brothers, and then left the family behind. And that family, and then the Iron Curtain comes down. He actually was never able to go back, my father, go back to see the other part of the family. Never. I mean, he was not able to go back. And I didn't see my other part of the family, the sisters, until almost I was like in the 40s when I actually met my real sister from mainland China, because we were basically growing up in two different worlds. Okay, so I was actually the first child born outside mainland China in Macau, and in fact that was a time where when you were born. I mean, there was no documentation, so I was the first one that actually have a birth certificate. And it's Portuguese, okay? I'm not Chinese, I'm Portuguese. I'll show you. So I was born that time, the first in a family to have a birth certificate. And I'll show you that. And born in a hospital and not born at home. So, and I actually, up to 6th grade, I went to a Catholic Jesuit school. Not because we were privileged, in fact, we were very, very poor. And I remember a tough time at that time because there's war refugees and you don't have money. And I mean, I still remember when I was young, there was 10 years. When I was 10 years, I have to wait in line for charity from the church. We got from the church. We have to wait for rice rationing. We have to get powdered milk, and we have to just wear hand-me-down clothes and everything. That's my childhood. Very tough childhood. Okay, basically. And then when I was 10 years old, the Lau family just immigrated. I use the word immigrated because there was, again, no paperwork, nothing. We just packed up the whole family and moved from Macau to Hong Kong. These two colonies, in fact, there was a lot of influx of refugees. They just cannot handle all that. So there was no paperwork. We just simply smuggle is really the word. Just go there and stay there and as illegal immigrants. So I was never a citizen of any country, of any place, and I've been stateless. In fact, in Hong Kong, they issued me a certificate of identity, and I was, the country, I was basically a stateless person for up to, I actually come to the United States. Imagine trying to get a visa to come to the US where you are a stateless person. Well, I did that. So my actually first actual state is United States, where I was naturalized after I graduated. So I've been a stateless person for a long time in my life. In Hong Kong, I went to what I call a progressive English high school. At that time, it was under colonial system. We still have the Chinese education system, and then we have the kind of the British, more progressive. And this one is even more progressive. I'll show you later, in the sense that they actually emphasize extracurricular activity. In the olden day in China, you just study, the teacher tells you what to do, and you just do, right? I mean, just study the old literature and things like that. But this is a very progressive school in which they actually hire English women to teach us English. And we are told that we need to go out there and do extracurricular activity. So that's where the high school I came from. I did well in all these public exams and all level of them. And you do good, you go to a better school. If you don't do well, you just stay at a not so good school. And I was, again, you have to go through admittance. I mean, people who from UK or something like that, I went through 5 years of high school, 2 years of ordinary level, A level. I mean, people from UK probably know about that education system. And then 3 years in universities. So I went through that, and I did very well in the entrance exam. And everybody, if you do well, you got all the A's, you go to medical school. That's my father's wish. So, but I said, no, not for me. So against of his wish, he wasn't too happy. I simply just took up science, math, physics, a double major in physics and math. And which means nothing to him. Was very unhappy that I should have a career in medical career, but I did not. So I majored in physics and math, and then I stayed an extra year in applied mathematics. And I was at that time, I was very much inspired by two Chinese physics Nobel Prize winners, Yang and Li. He got his Nobel Prize in 1957. That was the time. I remember kind of lining up in a lecture in the City Hall to try to listen to the lectures. And of course, at college, I read the Feynman lectures, like many of you did. If you're from physics, I really am inspired. And I decided I wanted to pursue a graduate study in physics. Okay? So here is the picture of the St. Paul's Cathedral, which is in the front page. And here's what it looks like nowadays. My house and my hospital is just right behind this historical icon. That's why I showed it, because I've seen it, and as a kid I play in this place all the time. Okay, so that's why this is what it happened today. Everybody go to Macau, they would visit this. Other than going to casino, they always they always like to visit this place, and this is what it looks like a long time ago. So this is what is left of the front, the facade, and the church was burned down almost 300 years ago. And here's my Portuguese birth certificate, my first in the family. So I put it in, and in fact, because my parents don't speak English, they don't know Portuguese, so all the names there are new, and even my name I spell in some funny way. I mean, you can kind of figure out the red one. And the most important thing, even the birthday they are wrong, because my parents used the lunar Chinese calendar. So for all my childhood, I thought I was born in certain days, and then I find out I actually have a certificate. I look at it, that's not my birthday. I mean, so that's why I have this identity crisis. I don't know what my exact name was when I was born. I mean, I kind of know that I was born in a hospital, but what day I was born. So I always confused about the lunar calendar and the regular calendar. So that's one. So this one is just a piece I never used. So, but then I find out it's there. It existed. Okay. Here's me. My family, 50s. chubby little kid. That's close to my house. That icon, my mother, my older brother. I mean, he was the baby that actually my father bring back from mainland to Macau, and he's actually a math professor in University of Hong Kong. So he's a math professor. So anyway, that's the whole family. Okay, and this is my high school in Hong Kong. And as I said, this is a very progressive high school. In fact, the name is the high school, they call it college. It's called New Method College. So this is somebody who actually came to the US, and actually the principal, he went to Japan and he learned all this new modern way of learning, which emphasize on gymnastics, extracurricular activity. And so the school is not known for its academic, but it's known for drama, and it's also known for the progressively shortness of the skirt of the you can see this is in the 60s, very short skirt. And then see, you can see that is the uniform that everybody, if you go to Hong Kong and talk about New Method College, everybody says, oh, they have a nice uniform for the girls, because that's known for. Okay, they actually find out the person who actually make this and design this, and I think we all feel that they actually take this after the principal over there went to Japan and they learned, and we always think that this looked like some of the Japanese uniform. Okay, but anyway, that was me at the end of high school, the graduation. It was here's my friend. It was the two of us who stick with science. He is now a distinguished professor at University of Iowa, and I'm staying here. So we are the two good friends starting from high school. Okay, so graduate school and early years. So 73, 74, I spent the first year and a half at grad school at physics department, University of Washington, Seattle. I wanted to major in theoretical particle or solid-state physics. This is after Li and Yang and Richard Feynman. I quickly find out this is way over my head to be doing something like that. And I want something, and then of course, this is actually also what happened at that time is that it was a very low point for the high energy physics and hiring. And I was told that, first of all, the average time to spend to get a PhD is like 7 years, okay, average time. And then I also learned that one of the students there, the older student, was in his ninth, getting a 10th year, the limit of his graduation. He started out from single, and then he married, had 3 kids, and he's now currently on welfare. So I said, what? I mean, this is not a physics that I was thinking about. So I was desperate. The switch is desperate. I want to get out, not physics. I wanted something practical to do. So basically, what is practical, and then my physics learning. So immediately the thing I think was air pollution. I was thinking practical air pollution. Maybe I have some physics in it. I don't even know weather is a science. I don't even know that all this wind and this monsoon thing, you can actually put it in as in scientific terms. So I quit the job as a TA over there and went over to the department. And then I actually find out that the professor there, who was an air pollution chemist, and he basically promised me a job where that I would be there, and then he would just support me. Well, it turns out after I quit my TA job, went over there and worked for him for a few days, he then one day he told me his grant didn't come through, so there was no support for me. Okay, so that I learned about the grant situation. So I was really desperate. And then I went to the department head over there, that's Jim Houghton. I mean, many of you know him. He was the department head, and I told him the situation. He said, okay, so let me see what happened. Come back to me in 3 days. So I spent the 3 worst days in my life thinking that I probably have to go back to Hong Kong now because my graduate career is over, because my support is done. But then luckily, he said he found that this new professor, Peter Webster from MIT, who comes in and work on monsoon. So he asked me, if you're interested in monsoon? I said, oh, definitely, because I I barely know enough geography to know what monsoon is. And I said, of course I love monsoon. I came from monsoon country and everything. So I got in the department and worked for Peter Webster. And then I met my wife in 74 and get married in 75, get my PhD in 77. And in fact, another story is that I was, this is kind of all this bifurcation in my life keep taking place, that you think of something and then something else happened. I was going to, actually I was get a job offer from Eric Krause. Some of you older folks probably know him. I mean, he's from Miami. He's an air-sea interaction. My thesis was an air-sea interaction. So anyway, so I was there, but then at the last minute, I have everything packed, labeled to go to Miami. Then last minute, C.P. Chang from Navy School said that, hey, we have an opening. Why don't you come and take a look? So my wife and I basically said, hey, why don't we just get a free trip down there to Monterey? I mean, it turns out one thing led to another thing, that we think there's a better situation. So we went back and accepted a job offer there. We just put the Navy School label on top of the Miami label, and we just drove down to Monterey, California, which is, many of you know, if you know the place, it's a really nice place. Once you get there, you don't want to leave. So my first exposure, in fact, those were the time where students never travel. I mean, I stayed in my graduate school, never travel, never attended meeting, and actually, I published one paper. I mean, nowadays the requirements are very different. But then towards the 1977, towards the end of my graduate school and career, and there was this first got the Figge monsoon experiment. And in fact, Peter Webster took me over there, and then there I first met people like Krishnamurti, C.P. Chang, Mencken Mac, John Young, Shukla, Sikka, and Kuttner, and all these people that really are inspiration for this kind of senior scientists in the field at that time. Well, Shukla at that time was also just freshly graduated, but he kind of think that he's very senior. Okay, so my work on monsoon cold surges, ENSO at the Naval Postgraduate School, I taught classes, and it's actually my first contact with uniform U.S. military people, and when the first time I didn't know that they have a ceremony. Every morning they would raise the flag, and then they would sound the bugle, and everybody had to stand their attention, and I would just keep walking, and then all of a sudden I said, what's going on? So it's very embarrassing. So the instinct like that, and I quickly learned that this is a very structured environment. The students are really serious because they have a limited time, and they are under a lot of pressure. So it's a very good experience for me. And so that's basically what I look like when I first got to UW. I never saw snow. This is the ski gondola I first saw. I just jumped on it and take a picture and got married. I was happy that I graduated. And this is a picture at the Naval Postgraduate School with Peter Webster in the middle and C.P. Chang. So two of my earlier mentor at the Naval Postgraduate School. Okay? So let's keep moving on. And this is the work I did at my PhD thesis. I mean, basically, at that time, there was just the beginning of GCM. And nobody at the university have access to GCM. And computer, we just have to do the punch card. So all my thesis is like 2 boxes of cards that every day I have to put it in and put it into the machine. And the machine sometimes chew up your cards, and you're in real trouble if you drop those cards, and all your years of work will be. So you punch every single card into it. And in terms of modeling, people are basically doing symmetric modeling, like Songnoli average models, Songnoli symmetric modeling. And Peter had this idea that, we should be doing something a little bit more, which would be a finite domain version of this symmetric model, which is, why don't we just look at a continent and an ocean, and then we also look at the continent and ocean. So we are getting into trying to develop a tool for monsoon modeling that we can run very quickly and learn something about it. So the nice thing is that I start from scratch, kind of coding the primitive equations in the atmosphere and learning about the ocean mixed layer model, and I couple them, and this is kind of developed this simple couple ocean atmosphere model, which we hope to be able to run for a long time. But of course, it takes so much time to develop, and the computer actually advanced much faster than the usefulness of this model. So by the time we finish, and after not too many years, I mean, it's much easier to do a 3D computation. So basically, not much come out of that, but I did learn a lot in terms of the coding and the primitive equation and how to do all those flux terms and the mixed layer processes. That got me into research in ENSO, which is so I was at the NPS for 3 years. And then I heard about this new development of the laboratory atmosphere in the East Coast, in this region, and big names like Chani, Lawrence, and then Joanne Simpson came to the Navy School to give a lecture. And at the time before, she actually joined the place, and I asked her, oh, what's happening at the East Coast, this institute? I said, oh, they have developing this new laboratory for atmosphere, and there was all these famous people were there, and so I said, hey, I mean, maybe I should try. So I basically say, who should I call if I want to inquire about a job at NASA at that time? So I say, well, call Mill Hallam. Okay, so if anybody know Mill Hallam, then you will know who that was. And if I know that was Mill Hallam, I probably would not call. I would not dare to call. So anyway, I called Mill Hallam, and we talked on the phone, and I get myself an invitation to come over here to give a talk. Okay, and then one thing led to the other. I mean, I'm not a modeler. I mean, not a GCM modeler, and that was Mill Hallam was the head of this modeling group with people like Shukla, and I think Dave Randall wasn't there yet. But anyway, all these high-power modeling people, and Mark Kane and Paul Schaff, and all these people were there. Eugenia Calnet, yeah, all these people. Yeah, Joe, you can, yeah, that's right. So anyway, I mean, so obviously I doesn't fit that modeling group. But luckily we have the climate and radiation branch. I have Al Arkin, I have Jerry North, Bob Cahalan, and people like that. I think they appreciate kind of not GCM type, non-GCM type of simple modeling and diagnostic analysis. So after I gave my talk, and then couple weeks back, I actually got a call. I got a job offer to be a civil servant at NASA. And at that time, I was still debating, should I go or not? I mean, I'm teaching, I like it, but should I go to this place or not? And then this is a time where the transition of the government, the Carter government is coming out, and Reagan is coming on top. And then, so I'm still debating to come or not. And then I heard that Reagan is going to come January. And when he comes, he's going to freeze all government hiring, and he will rescind all the offer that has not been accepted. So my wife and I said, okay, should we do it? Should we do it? I said, okay, let's do it. So we do it, and I call up and say, I accepted the job offer. So I actually, 2 months later, I just packed and I drove across the country with my 9-month-old daughter at that time, and we reported to duty to NASA on February 14, Valentine's Day, 1981. So I remember that day exactly. And the funny thing happened is that I know I was the last one being hired at Goddard at that time, because several days after I got in, I got a call from the administrative office, code 100, and say that I need to go to the building 8 to do something. I said, what is it? And say, okay, well, it turns out they have a tree planting ceremony, and they were looking for the most senior person, the person who's high, and the most junior, the latest hire. And I was obviously the latest hired one. And I actually helped to plant that tree in front of Building 8. I can point out to you which tree. I can still remember that. So that was interesting. So I was the last one before the hiring freeze got shut down, and was last to get in under the wire. And so that was the interesting time. I say that for that first 10 years was a Goddard. I do nothing but research, publish, and publish. Okay, that was really the best time in my life. And I was able to do, because I come from academia, so I naturally immediately make connection with University of Maryland, and then I was able to teach a course over there and have some students, and I even wrote a joint NSF proposal, and I get money, and I have a postdoc at University of Maryland, and I support graduation. It was really nice. It was easy to do at that time. And then I was able to collaborate. I traveled quite a bit at that time, start to travel to China, to Korea, places, no restriction. And I published like mad, 45 papers in like 10 or 11 years. And I work on ENSO theory, which is, I'm kind of a theoretical person by nature, so I like to know about things. So I work on coupled ocean atmosphere instability. In fact, I was the first to propose the coupled instability in ENSO. This is before George Philander, which I think he got all the credit for putting up the paper. But in my 84 paper, I already point out coupled ocean atmosphere instability is an important concept in ENSO. And also, I also write a paper on the stochastic nature of ENSO, of the fast frequency forcing by the low frequency component of the atmosphere, which is the MJO, which I come back to. So we wrote some kind of a classic paper in there, and then I devoted a lot of time when I was at Goddard to do this 40 to 50 day oscillation. I'm going to talk a little bit about why I do that, because as you know, if you look at my training, I have zero training in remote sensing. Why NASA actually hired me was still a mystery to me these days. Okay, so since coming to NASA, I have to work on remote sensing. So the only thing I know is OLR, outgoing long wave radiation. That was at that time a NOAA product, AVHRR, and then they had many years of them. And the only thing I know about OLR is that if it is low value, it means it's probably some deep convection in the tropic. If it's high value, because the lower cloud, then it's less convection. That's really the only thing I know about OLR, nothing else. So I was here at NASA trying to use satellite data, and in fact, I'm going to go a little bit about history about this very important phenomenon that at that time known to be the 40, 50 day oscillation, but then later on it became this MJO, which now you heard about. There's thousands and thousands of papers written on this phenomenon, the MJ, and so I'm going to talk a little bit about that, Asian monsoon study, and also because of my work early on in tropics and later on convection, and then I start to get into this idea. At that time was how a mission comes about is very interesting, because basically it's one day John Theon from headquarters walked into Goddard and tell us, hey, we have this $200 million, help us to spend it, give us the best idea of what you do. This is basically how this idea, and of course there are competing ideas. The idea, because Dave Atlas was a radar person, obviously, he's interested in rainfall, and then I have Jerry Knopf, Tom Mulhey, Otto Tilley, and then we recruited Gene Rasmussen, Joanne Simpson, and then Marv Geller, and I contribute a little bit because I was just a junior scientist at that time, and so this is where the TRIM idea started, tropical rainfall, and this was also the time Dave Atlas, Marvin Geller took place, and it was really heady times for me because before I was 40, I won the AMS Meisinger Award, I won the NASA John Lindsay Award, a feature in magazine, so I'm on top of the world. But then something happened which is really have a lasting impact, which is the Space Shuttle Challenger disaster happened. I remember that day, I was in my office, and then everyone said, oh, something happened. We all rushed out, and then we actually watch on TV. That was a major impact. It has a major impact mainly on engineering, safety, and the workplace at NASA. Luckily, Earth science is not so much affected. In fact, as the next decade show, Earth science is on the rise. This is going into the golden era of NASA Earth science, which I actually present. So basically, that's where I came in. Oops, in terms of the organization. This is a chart that Chuck Cody gave to me yesterday when I was asking him. Basically. So this is actually, if you look at the chronology, before this laboratory of atmosphere, this is Dave Atlas. This is where I come in. And then before that, actually this is not 4 organizations, all one organization. The timeline is here. Okay, so it just keeps changing names. There's some meteorology, there's aeronomy, and then obviously at that time at NASA, there's some work done, but they couldn't decide what the name is, and they keep changing name. The Laboratory of Atmosphere and Biologic Science, Laboratory of Meteorology Science, all these are just sequential. And then by the time, and then they actually split into the planetary side and then the hydrospheric side. And then Dave Atlas come in, he started this, and then the stratosphere get absorbed. And then for a while, then the space science kind of spin on their own, really doing space science. We are called the Applications Directorate, which is kind of a dumb name. I mean, we don't like that at all. We're just applications. It's not science. So anyway, after a while, they actually changed it. And then the Atmospheric Science Lab split into the Laboratories of Science, Atmosphere from Marvin Geller, who's the head of that, and then split into the Ocean and Ice branch. And then we have the Laboratory of Atmosphere. Of course, later on, I didn't modify this chart. Later on, this one also disappeared, which is kind of sad because I started from here. I would like to see this continue, but then this is gone, and Franco Rinaldi and I took over from here. Okay, so this is kind of give you an idea that at that time things just grown organically, and there was nothing, until in the late 70s and the 80s before they actually formed this laboratory for atmospheres. Now, I'm going to come back to this idea that when I first come in here, I have this OLR picture. So what topic should I be working on? So this is the time in which this is the classic paper by Madden and Julian. They published this in 1972. This is one of the must-read paper by any graduate student who want to do spectral or climate analysis. This is one of the most elegant paper in terms of a spectrum and co-spectrum analysis using limited data and combined with a lot of imagination, which turned out all to be correct even these days. This 72 paper where they use station data, do a co-spectrum analysis, and this one shows the phase line. So basically this phase line indicating things progressively move from the Indian Ocean to the Central Pacific and tend to fan out that way. And then they come up with this picture that this pressure wave that involve both convection and wind that are propagating from the Indian Ocean to the Central Pacific disappear, and somehow it was able to revive itself. So this paper was published in 1972. And it was never referenced at that time. Nobody paid attention to it. And so what? You find a phenomenon. So we find phenomenon all the time. But I think when I saw this picture, I see convection. Oh, and then I thought about OLR. At that time, we had like 8 years of OLR data. And then I said, hey, maybe this is something that is really fundamental. And so I start working on this. This is not a very good copy of it. So this is published at the front cover of the Bulletin of American Meteorological Society. And basically the idea is that this 40 to 50 day oscillation we think is the fundamental, very fundamental part of the tropical system. And together with ENSO, we kind of say these two phenomena are not necessarily disconnected. In fact, they are very much part of it. I remember when I gave this lecture many times, I use this expression, and I think it's get a lot of attention, is that I said the 40 to 50 day oscillation is the heartbeat of the tropics, okay? When an El Nino comes, you have a heart attack, basically. The tropic has a heart attack, but every time it was able to recover. So I think that caught on a lot, and in fact, that was lead to a flurry of activity in really looking at the tropics. And I don't need any sophisticated statistical tool. I just plot 8 years, or this 10 years of OLR data. This is not very good reproduction. I couldn't find the original. Of a time longitude section, so you can basically see, I mean, it's hard to see it right now, but you can see kind of propagation. This is the eastward propagation, and then you can see this heartbeat every year. It keeps coming on, and then the OLR shows that this is an ENSO signal. You can see the negative here means increased convections. You can see this convection increases from the dayline all the way to the Eastern Pacific and the Eastern Pacific region. So now we know this is basically an ENSO signal. But what the new idea behind it is really this ENSO, and also is a fundamental part of the 40 to 50 day oscillation, now called the MJO, is a fundamental part of the tropical oscillation. And I continue at that time the work on the connection between the planetary interaction associated with East Asian monsoon. And this is the picture we've drawn about how things happening in the exotropic come in, excite the enhanced convection in the maritime continent, and lead to the transient fluctuation of the local Hadley and the Walker circulation. And this picture actually was modified and adopted in the early TRMM document. I was trying to find this document. I couldn't find it. If anybody actually have this document, please let me know, because I know they have Joanne Simpson, and we talked about this, and she modified it. We have a picture of that. So that was in the TRMM document in terms of trying to look at the tropical, extratropical interaction. Okay? So this is the second decade. Now at NASA, 1991 to 2001, Marvin Gaylor left, Frank Rinaldi took over as the chief. Al Arkin retired at that time, another one of my mentor. He was a branch head. I actually, at that time, as I said, it was, I got job offer from different places, and I actually went and got an offer as the head of the department at Texas A&M. This is something, but then at the same time, I was I mean, people, I mean, arguing, convinced me that I should stay behind. So I actually turned down that job because Jerry North went over there. He wanted to take me over there too at that time. So I turned down that job, saying, hey, I got better thing here at NASA. So which is true. This is the entering the earth science, what I call a golden year. And actually, golden, we're administrator name is also golden. Okay, it's actually fits quite well. So NASA became much more organized in satellite missions. I mean, this is the EOS mission. There was a strong interaction with scientific community, seeking advice and working with the so-called payload community, and I was a member of that. I was a member of the payload community through my IDS investigation. And there was a huge increase in the NASA Earth science budget. In fact, comparable or even exceeding the space science. And we have at headquarters very visionary people like Shelby Tilford, Len Fitz. I mean, people, if you still remember those names. And when people thought Shelby was crazy, and he said he's going to develop this big EOS program. He's asked Congress for $20 billion to study this entire program. Everybody thinks that he's crazy. Well, he's not. He didn't get 20 billion, he got 10 billion. Okay, so, and that is how kind of visionary at that time headquarters was. And then they got, of course, his idea is that you put everything in one big satellite, and of course that was when it the community, no, you don't want to take that kind of risk. So they chop this off into Aqua, Terra, Aura, and many small pieces, which is kind of the right way to go. So this is where NASA really become organized in terms of satellite mission. And then at that time, TRIM was launched in 1998. And I myself was actively involved in field campaigns. I was involved in the Toga Core field campaign, South China Sea monsoon experiment, and then I'm going to quickly to go over something. So this is the Toga Core campaign I was involved, and this is following the work on Toga, and also on the MJO, where we're trying to get signals of the Western Pacific. And this is some experience. I mean, I definitely recommend as a scientist or working in the science area to be involved in your lifetime at least 1 or 2 field campaigns. You learn a lot from that. And in addition, I learned how real seasickness means. I mean, I was on one of those ships, and then I've never experienced the real seasickness. In the pressure inside you is just horrendous, and then you just got to everything just comes out. It was, I mean, actually, I was not the only one. It was like half of the ship. We were actually right in the Southern Ocean trying to get across to the New Caledonia in that place where we stationed. But that was some experience. I learned a lot, and I was on the science steering team in there for the atmospheric part of it. And Peter Webster was the head there, of course. So I learned a lot. And then that experiment, a lot of you know about that. And there was some science in there. I'm going to skip on that. And then the next experiment, which I actually involved as the chief scientist, is also, well, it's unique in the sense that the South China Sea experiment, we have the involvement of all these countries around the South China Sea. If you know the politics of the South China Sea, you know this is a very sensitive place, especially nowadays, okay, in terms of the relatively territorial claims by Vietnam and by Philippines and China and Taiwan and all those places. We actually get all these countries, including the US, to work together in 1998 to actually do a scientific experiment focusing on the onset of the monsoon. And the interesting thing, we have the US Toga radar, which is Otto Thiele had it, was mounted on board of a Chinese ship. Imagine this happened these days on a Chinese ship in the Xisha Island, in the most contested part of the island. And then we have the military from the Taiwanese, the Republic of China, was on the Dongsa Island trying to kind of communicate with people, and we have people from the Taiwan side on board of the PR ship, and they were communicating with the military over there. And it was just, in fact, we got a lot of press. I got a BBC reporter asking me about how do you guys do that? I mean, so that was not only a scientific first, but also a political first. And in fact, I was searching, okay, this is the setup of the experiment. We have aerosondes, we have ground-based radar, we have network set up to do the budget and things like that. So that was a very interesting period. I was searching the web for trying to find that article I know the BBC reporter wrote, and I couldn't find it. Then I find something else. This is very recent. This is October 2013, which is an intelligent briefing. This is an open literature by somebody associated with Homeland Security Department. And I just noticed that because I was putting Sysmex in there and trying to see, and then this one is that because we were saying that we need to use satellite to monitor that whole program, and then now you read it. It's basically said is that satellite images are well suited for environmental monitoring, particularly in the maritime region, in the South China Sea, and things like that. And then a precedent for cooperative monitoring, it actually referred to our work. For specific purpose, exist in South China Sea. In 1998, nearly a dozen countries, including several spread island claimant countries, that's key, China, Malaysia, Philippines, Taiwan, Vietnam, and other countries, Australia, Indonesia, Japan, Singapore, Thailand, and all cooperated in this Sysmex, South China Sea monsoon experiment. This cooperative activity took extensive meteorological oceanographic observation during satellite, aerial, on surface data to better understand the dynamic of summer monsoon patterns. So this has been said and actually referred to in the most recent, basically they're calling for, as what we did call for that, at that time, NASA satellite observations is important, it's neutral, and we should all be doing that. And said this should be a diffuser of all this tension in that region. Everybody have their own interest. So I was interested to actually find out that article. And then when I do science, we have to deliver something, and I also said that a lot of the discovery are mixed surreptitiously, that you set out something to do and you move on to do, and you actually move the sideline to do something else. So actually my most cited paper is not my work on MJO, not work on monsoon, it's really this paper. I think it's because I come up with a good name for the title. I say, how to make a time series sing. Okay. So if you read that, the motivation is very clear when I do this. So it's since introduction by Moret, because remember I have a degree in applied mathematics, I'm interested in mathematics, by Moret, this is a French mathematician over a decade ago. Wavelet transform has found wide application in many different fields except atmospheric science, basically. And it seems somewhat befuddling that there is still a dearth of use of wavelet transform research on climate signal detection and analysis. So that's the motivation. So we basically, at that time, a mathematician worked with me, Henyi Wang from mainland China, and she's a mathematician, and she's also a musician. So she said, wavelet is just like music. It's just like music. So you can make a time series into a musical piece. And then she showed me that's the way it is. So basically, if you look at the kind of things we, in climate analysis, is that we talk about amplitude modulation, we talk about frequency modulation, we talked about sudden change in frequency, abrupt change in frequency, we talk about abrupt change in time. All this actually, in a wavelet transform, has characteristic signatures, okay? Amplitude modulation basically stay the frequency the same. If it is a frequency modulation, you can see that modulation very clearly. If you think of this as the musical note, this is just music go up and down. And if you think of this sudden change in frequency, this is basically change one octave from this one. This is 2 to the power scale power 2. So you just come up this way. And if it's a sudden change in time, it has this kind of signal. So we basically analyze all these signals and come up with a real application. This is applied to a long-term time series. This is like a 2.5 million a year time series of oxygen 18 somewhere, I don't know, from the ice core. And so we look at that, and then we actually wrote this paper where we describe the tool. And then we actually say that we actually identify this 40,000 year and 1,000 year cycle from the Milankovitch cycle in the ice core. We also identify various signal in the climate change signal. So I think after this, I mean, now this has become a common tool. And I think that paper probably have a lot to do with it in terms of actually introducing this idea of nonlinear time series and its applications in climate change. And also did some work on AMIP, which I'm going to skip. I'm going to skip to the third decades, which is from here to there. And actually, I got actually a lot, university position vacant. I got a lot of, I went interview, University of Maryland. I was competing with Johann Kelney. I didn't get the job, so. And then I went to FSU, I take a look at it. I don't like the place, so I don't go. I go to University of Hawaii. I wanted that job. They didn't give me that job. They gave me another job. I said, no, I don't want it. So in a way, if you improve, if you know, it's nice to know that you have a choice, okay? You make a decision in terms of where you want to go and stay. So second chance, I stay. And at that time, I actually happened to be around about the time, so I decided that I want to basically take over that. And then in 2003, they were in that era. This is the major hitter in terms of NASA. This in 2003 led to a major technical and organization change in NASA. Okay, and then we have the combination of space and science directory combined. We have the full cost accounting and everything. And then I was very busy spending on workforce alignment, attrition, hiring, and we actually get rid of some quote unquote dead woods because the good thing is, of course, we have some collateral damage as well. So we need to repair that, and we hire. And so it was a very busy period, an exciting period still. So I continued to do work on rainfall, climate connection, and then I actually, at that time, I wrote a book. I actually compiled a book on intraseasonal variability of tropical ocean atmosphere, and then the early result from EOS, very exciting results where I started to actually get into aerosol water cyclodynamic interaction. So I think I'm going to quickly go through this. Here is basically one of the work that I did. I think is still not start to get much attention because we are the first one to actually just document that. You don't look at the total rainfall change, you look at the change of the characteristic of the rainfall, where this is where you start to find a signal. So we simply use something called quantile regression. Instead of looking at the trend of the total rainfall field, we break it up into different quantiles and just look at the quantile change in the light, moderate, heavy, and very heavy rain. So you can see that as time changes, this heavy rain signal is huge in this thing. So heavy rains get heavier, and actually drought area gets drought, and then there was a compensation. So the rainfall spectrum does not respond like temperature tend to be a translational response, but rainfall tend to be a flattening response. You got both wings. You got the enhancement on one end and the other extreme. So floods and droughts are necessarily related. So that's the starting opinion, and actually that fit to some of the later work we do. I wrote this book. Well, I compiled this book, the chief editor with Dwayne Wolitzer. The idea is that we quote John von Neumann, who is the father of NWP. He basically said, approach is the first try short range forecast, and only finally to attempt forecasts of medium range period, which are too long to treat by simple hydrodynamic theory and too short to treat by general principal equilibrium theory. And this finally takes almost 50 years because we don't, at that time, we don't know, don't know a scientific entity, entity that actually gives you that kind of a low frequency signal. The MJO is one of that scientific entity. It's not an imaginary stuff, it's a real stuff. And once you have that, we decided this is the time to actually write this book or compile this book for a one-stop shopping for intraseasonal variability. And so this is the first edition in 2005. The second edition also come out in 2011. So it was one of the most read downloaded ebooks in that series. And many of you probably heard about this, so I kind of venture into aerosol because there's a lot of aerosol data, and everybody working on aerosol those days. So being trained as a dynamicist, I was looking things at always a different point of view. Is really from a dynamical point of view. So we basically come up with this, what I call the elevated heat pump hypothesis, which is one of the key hypotheses that people are still testing with all kinds of field campaign experiment. The idea is very simple. A monsoon, if you don't, a clean monsoon without considering aerosol, simply distinct by the total lower pressure, drop, wind in and strong wind force southwesterly flow, and then you have the monsoon. I mean, that's very simple meteorology 101. When you add an aerosol in the kind of right way, at that time, I have to say something about this. When I get into this, because there was not much data, and the information available is so confusing to me that I really don't know where to start. But it turns out we have the go-kart model. Min is here. I mean, I have to credit her well in coming up with a 4-dimensional distribution of the aerosol distribution, which at least is somewhat close to the climatology. And we basically stick this into the GCM, at that time the FV GCM, and then take away the radiative effect and then put it back on and see what's the impact. The nice thing about this is that we actually have a close to observed distribution of the aerosol. We put it in. If you let the model run free this day, the model is still very hard to get that even approximate distribution, the timing. And if you put it in, it turns out the circulation drastically changes, which is simply that the aerosol produce an elevated heating, which actually locally it would suppress rainfall, which is rainfall supposed to be happening here, will suppress, and then that moisture is being transported into the region in the Himalayan foothills. So you can see that basically this is another interesting case in which the model prediction went ahead of observation. Okay? I mean, so that's why I have a lot of difficulty publishing this paper. It was first reviewed in Science, and the two reviewers come back. Obviously, one is an aerosol guy. I mean, they've been looking at all this local effects and say, the top of the Tibetan Plateau have no aerosol. How can you get heating over there? So that's energy inconsistent, so reject, okay? So that was really disappointing. And then another reviewer, obviously the monsoon meteorology, said people have been studying monsoon for 100 years, and they know about this dust in India. I mean, nobody talked about this, so this must be wrong. I mean, there's no data, okay, so that must be wrong. Reject, so very disappointed. So I think, but then it turns out I persevere, and I try another journal, and I actually talked to the editor, explaining to them what this was, and it turns out it got published. And it turns out this is kind of one of the major contending theory now. Of course, there's a lot of debate still going on on whether or not this actually works. And because it goes against Ramanathan's idea, which said that the aerosol actually weakens the monsoon. We say it actually strengthens the monsoon first, and then the self-interaction weakens the monsoon. So it's a different tune to it. But I think there's still ongoing debate in terms of how the aerosol would affect the Indian monsoon. And then from that on, we actually try to get the community involved, talk about this joint aerosol monsoon experiment, publish a BAMS paper where we basically say that understanding the physical processes responsible for aerosol monsoon water cycle interaction is fundamental to improving prediction and enhancing the vigilance of climate hazard in Asian monsoon regions. Okay, so we use a lot of satellite data. We use CloudSat Calypso. We use MODIS. This is something I borrowed from Sichi Tai, and just map out. I mean, this is definitely, and as you can see, the aerosols are being piled up in this region and this region, and all the way up this region. That's why I call it this Tibetan Plateau region turns out to be very important in helping the aerosol to pile up and keep accumulating to the point that it excites this heating effect. That's what we think is happening. And then we actually, some of us, Sichi, myself, and Brent Hoban actually went over to work with the Indians in the foothills and put up the observation station. This is part of the JMAX 209, where we actually make some measurement over there. So I'm going to talk about the 4th decade now, quickly. So time is running out. So the Earth Science Directory reorganized. So the name of the laboratory, Atmosphere Disappear, against my objection. So no use. And Peters and Manias. Yeah. So I guess as soon as Franco resigned, that happened. I think Franco is kind of the person who is holding all this. And we know it's coming, and the branch become lab. I become the deputy director. I guess the functionality, we didn't change. I actually acquired additional duties is to work with the Wallops, which has been very nice. I mean, at first I thought, oh, another management come under me. But then it turns out it actually is very good. I think this is very important that we have the connection with the Wallops flight facility in terms of our aircraft fuel campaign. And as you know, there's a lot of change in leadership here at 610 AT. I mean, out of the three labs, I have two new lab chiefs, and I have a new associate deputy director. And then, of course, we're also expecting new changes in 610 as a whole. We have a new GMAO person, and Peter is leaving, so we might have somebody else, and all those things. So there's a lot of that activity in the early part, and I continue my activity. Actually, I was asked to serve on this National Academy board on the Himalayan region, because the work on the elevated heat pump, basically one of the hypotheses is that it actually accelerates the melting of the glacier in that region rather than global warming. And so that was in one of our paper we wrote. And then I was served on that. We published the second book, and I was more service. I was elected president-elect of AGU. I'm going to serve. I didn't know it's a 4-year commitment. I mean, and didn't tell me when she. Yeah. So, but anyway, I'm glad I'm in. More surface work, and then I continue my interaction and aerosol, water cycle IDS, which I just find out I did not get funded this time. So anyway, I'll do something else to take my time. Okay. Anyway, so this is the aerosol monsoon climate work. I'm going to also say that I actually work a lot with the glaciology community, high mountain glaciology community. This is a chart produced by Jeff Cargill, who is the mountain glaciology, and he basically adopted this idea of that this entire region has a lot of climate and glaciology differences in terms of 1, 2, 3, 4 region. And then we work to say some of the region may be affected by this EHP, others might not be, so like the central and this region is free from the EHP, and then there are other factors that actually cause the glacier to grow in this region. But most of the glacier in this region are actually receding and disappearing. So the question is whether it is aerosol or greenhouse gas, or if it is aerosol, it is due to atmospheric heating, or it's due to the snow darkening effect. So a lot of interest in there. In fact, I was now a team of a JPL team to actually look at an EV proposal to actually look at that problem. So this is the NRC report. I was a member of that committee, and that committee, there are many other things that we recommend. Basically, this is to narrow down the uncertainty, and we need improved measurement of key climate forcing response of the Himalayan region, the cryospheric climate, and the social system, which is the water system. And this includes not just glacier, but snowpacks and all the seasonal melting as a whole. So my second edition of the book came out. It made the top 25 list in the Springer series, as there was like 1777 downloads on the ebooks. And I just quote in there, the first edition, we added new chapters and revised the chapters here in this. We added a new chapter of the EOS, the satellite era, in terms of how it impacts the understanding of the MJO and atmospheric phenomena. Basically said that the EOS satellites from NASA really make a big leap in terms of making a better understanding and of that. So that's something. There was a book, and then now this is the kind of things that I'm interested in right now, trying to make a connection between floods and drought. We wrote this paper on connecting the 2010 Russian heat wave to the drought. And so this is something that more recently, and some of you probably know that I'm a practitioner of the Chinese Tai Chi, okay? And then so I'm well versed in this idea of yin and yang, and also the Qi. And then the way I see it is that this is kind of, you can call it a philosophy, a Chinese or something, that every natural system, including the human body, has this yin and the yang part, okay? They always oppose and try to balance. If something goes one way, the other one, something always happens, and you have to be connected by something. So this is the qi inside your body. So if you look at the global system as a whole, the yin and yang part is a flood and drought. They're the necessary consequence. They don't exist on their own as singularity, but they are part of that system. And the qi is a heavy circulation that really links the flood and drought. So there's no randomness. Well, that's obviously randomness, but there's not entirely random. Floods and drought occurring is governed by this system, which is the part of the heavy circulation. And this is kind of the following up of the work we already published. And early this year, we published this paper, which made a lot of news in terms of looking at a canonical response, a rainfall response. This is all model. This is from CMIP 5 model. And we recently submitted a paper which is basically say a robust response to heavy circulation to global warming. This is, has been submitted, and I'm going to skip that. In fact, if you remember this, this figure I showed earlier on the observation, we use the same thing and say, can we see this pattern in all GCM? It turns out, yes, all the GCM are telling us that the very heavy rains are responding to climate change much faster, and the heavy rain, the medium rain actually reducing, and the light rain and the drought area actually increasing. So all the models, this is like 33 model we look at. I mean, you can see the sign. They all tell you that this is happening globally under global warming. And so let me see, I'm going to skip that. And in fact, this is all the science. This is the last science slide I put. This is something, basically it's what happened. If you look at the heliocirculation, this is climatology. So rising motion, heliocirculation, subtropics, ferrocell, and then the polar cell, okay? So under global warming, what happened, what we are thinking happening, and this has to be validated by data, by TRMM data, by GPM data, and actually could be a driving force for our next round of GPM science work. I mean, what this model are telling us is that the tropical convection becoming deeper and narrowing the convective zone. So this one become narrower. And as a result, you produce dry zones in the land region, like in the Amazon region and part of African region, on the land region. But then the entire helicirculation, the center of gravity rises because of deeper convection. And then because it rises, it's going to go further and it comes down longer. So as a result, if you look at this as a subtropic, the subtropic is get expanded. You would create new drought area in the tropical region, as westerly expanding the tropic, both mostly northward, and as a result of that, you actually get a weakened circulation, which is the hypothesis governing that the overall the helicirculation could be weakened, but it is actually enhanced rainfall and deep convection in the tropical part, and as a result you get this expanded, and as a result you push the polar front and the jet and everything. So this is the chi of the system. This is the helicirculation. It's actually responding. So far, nobody has come up with a clear signal of the response in the global GCM. I think we're the first now to come up with this idea. We call it a robust response to helicirculation, which I think would have important implications in terms of flood and drought distribution and things like that. So I'm going to wrap up here. Looking forward, we'll continue delivery of high-quality data set from EOS, excellent science from EOS satellites. And I want to mention two of the existing ones, MPP, and then another one is the total solar irradiance. That is something, I mean, there's a AOR for the MPP science team, so this is very exciting. And then the next thing coming up with the GPM launch in February 28, and we have technology opportunities with the International Space Station, CATS ISS launch. This is Matt McGill, is he in the audience? August, and then the major challenge is to me for the atmospheric AT is that the lack of a flagship atmospheric science satellite mission after 2018. We have a void, but we have lots of things to do. The research frontier for the next decadal survey I can see is changing characteristic of rain cloud system under global warming, aerosol cloud or cloud precipitation, no matter how you break it up, in interaction and atmospheric chemistry, climate interaction. Those are really the frontier area. And we have the means to do it. I mean, even though we don't have a major, I mean, we'll continue GPM work, obviously, but even though we don't have one, we hope the next decadal survey would help us to get one, is the Earth's class ventures, the suborbital, the instrument, and the mission. And then we always have the field campaign, airborne science, instrument flights. And of course, we have modeling tools here too. I mean, we have the great modeling GMAO, we have the aero mirror analysis, and we can also play with the GIS Model E. And in addition, we have very high resolution regional climate model for high impact weather study, the kind of work that TAO is doing, and a number of other people, Krista is doing, and climate attribution studies. And we need high-level involvement in international programs, such as IPCC R6, IPCC CME5 analysis, NASA satellite, and then of course, being atmosphere, we also have to be interdisciplinary. I mean, there are upcoming ISAT-2, SMAP, and some of us even on the atmospheric science community would get interested in it. So I'm going to stop here and come up with my concluding thoughts. At this point, it's a blank slide, okay? So people ask me and ask myself, why I come to this point in my life, and how did I do it, and all those things. And I think I come up with the idea. So this is in a way, I don't know whether it is preordained or I'm brainwashed or something, but I can always find examples in quotation from my own learning. So this is your fortune cookie moment. Okay? All right? So I will speak to it, and I think a lot of people here would understand, okay? So this is basically the hierarchical thinking in the Chinese learning. This is self, this is family, this is country, this is the world. Okay, basically they said, I mean, this is, you have to improve yourself, self-integrity, self-whatever, knowledge, and then you have to have a good family. You have to, then you can rule the country, then you can conquer the world. I mean, so this is hierarchical thinking, okay? You can think of it, everything, of course, in the Chinese system, the individual is kind of subsumed under all that. So it's really refreshing for me to come to North America and say, it's kind of the other way around, it seems to. But sometimes you do have that also. So in the US, your individual definitely a much bigger role. But in the Chinese thinking, it is the element of that. So this is 修身齐家治国平天下. Okay, that's, I didn't learn, I mean, didn't do this, but it just, well, come to think of it, maybe I'm brainwashed to be thinking like that. Okay, second one. This is actually really good. I mean, in terms, so the Chinese people all know that, right? If you do good in your learning, go and work for the government. Literal translation, because in the Chinese system, the working for the government is the highest honor for a learned person. So this is the teaching, is that you go for the work for the government. I didn't know that, but maybe I'm brainwashed into thinking about it. Okay? So this is this idea of the Chinese thinking, is that there is always a small me and a big me, okay? Which means that things immediate to yourself and things has to do with the institution and the things surrounding you. And the philosophy there is that in order to achieve good, you have to sacrifice the small me for the big me, okay? So this is, to me, oh, maybe I do a little bit of that, not all the time. So this is a very kind of, to me, it's kind of the deep thinking. I mean, I can come up with that. And finally, is this one, okay? I think the Chinese people here will know. This basically say, this is actually a story. Should I tell that story? Oh, this story is very famous. This old man, his name is Chai, same as Siqi. This old man Chai, he is as a living, he and his family raise horses in the northern border. It's a story from many years, an ancient story. So he raised, his family raises, and one day his son come and tell him that, oh, Dad, this is really bad because I lost a horse. The horse just went away. I just missed it. So the old man said, oh, don't worry. I mean, these things may turn out okay. So it turns out a couple of days later, the horse come back, not only on his own, it actually bring another horse, comes back. And this horse from the nomadic tribe is a really strong horse and everything. So the family was happy. Basically said, you lost something, you don't know, don't be sad, you're going to gain something. Okay, the story doesn't end there. So the son actually likes to ride the horses, so he tried on this new horse and everything, and then he was riding, and then he fell and broke his leg. And he felt really sad. Okay, the father said, no, don't worry. I mean, something will maybe happen. Don't worry about that. Oh, it turns out that was a time of the war with the nomadic tribe in the northern part, and they were looking for a young man to fight the war. And of course, he broke his leg. He didn't have to go to the draft and fight the war. And it turns out that was a really tough war. 9 out of 10 people get killed in that war. So he's happy afterwards because he didn't have to go to the war. So the moral of the story is that you lose some, you win some, and so you never really give up hope. And because some of the things you lost may actually help you to get things in the future. So next time when you get your proposal rejected, get your paper rejected, which I have my share of it, don't worry. This is going to build you up for the next round of winning. So I'll stop here. Thanks.
Because of time, I'm going to allow one quick question and then we'll stop there. Any burning question? Yes.
So we are just one question. Why the like a monsoon takes place in those particular places, like not other places, like Florida? Why we don't have a monsoon over Florida?
Well, I mean, the first thing you think of is the land sea distribution really contribute to the different way the monsoon works. So if you are in a system where you have a large continental stationary forcing that coupled with the ocean, you change the land sea condition, and as a result, you would get the monsoon. Now, the U.S. would have something like a monsoon, but it's not persistent. To be a monsoon has to be a persistent prevailing change in seasonal wind. You get a little bit of that, but too many transients are happening because the U.S. continent is covered by two oceans on the side, and then it has a lot of extratropical influence. So you don't meet the definition of a monsoon climate, which is a prevailing wind and a sudden onset of rainfall. Yeah, which there's a big debate whether South America actually have a monsoon. In fact, we wrote a paper about, the title is, does the South America has a monsoon? The conclusion is yes. I mean, basically they have the elevated heating, they have the reverse. Well, they don't have the reversal, but if you subtract the seasonal mean, you subtract the trade wind, they do have a reversal. So that's where you fit that definition.
Okay,
Yeah.
let's give Bill the final round of